Welcome back to the Deep Dive. Today, we are tackling a problem that I think, well, pretty much anyone working with AI in 2026 has banged your head against at least once. It's what I like to call the cloud dilemma.
Oh, yeah, it's a very real wall to hit.
Right. You want that raw power of the massive models, the ones that can, write poetry or code an entire app in seconds. But then reality sets in. You're dealing with data privacy risks. I mean, do you really want to send that proprietary code to the cloud? And then there's the network latency and, let's be honest, the spiraling costs of those API calls.
Exactly. It's the trade-off we've all just sort of accepted for the last few years. You either get smart and expensive in the cloud.
Or dumb and cheap locally.
You got it. That was the choice.
But what if you didn't have to choose? That's what we're exploring today. We're looking at a really fascinating technical deep dive by Kin-Fei Lo, a senior cloud advocate at Microsoft.
And this was published on the Semantic Kernel Dev blog, so very recent.
Just recently, yeah, February 2026. And the timing is perfect. It lays out a solution using something called Foundry Local, combined with the Microsoft Agent Framework, or MEF for short.
Right.
And the mission here is wild.
Yeah.
We're talking about building deep research agents. So systems that don't just chat, but actively research, judge their own work, and report back.
All running locally, on your own machine.
On your own machine. And that locally part is key, isn't it?
It's everything. We aren't just talking about running a chatbot offline to save a few bucks on tokens. We're talking about orchestrating a complex, multi-step workflow that, well, it mimics human research without a single byte of data leaving your hardware.
That sounds almost too good to be true. Complex AI without an internet connection.
Well, it's the direction the industry is heading. We're moving from just calling a model to building agent workflows. So let's unpack how Kin-Fei Lo suggests we actually do this.
Okay, let's start with that landscape. The article sets the stage with this tug of war. We have the cloud models, powerful, but with all that baggage we mentioned, and then we have local small models.
Right. And historically, local models were, let's say, the lightweight cousins. They were great for privacy because they lived on your device, but they just lacked the infrastructure to do the heavy lifting.
You couldn't chain them together easily.
No, not without writing a mountain of custom code.
Enter Foundry Local. Kin-Fei describes this not just as a tool, but as an extension of Microsoft's AI ecosystem to the edge. What does that actually mean for, the listener?
Think of the edge as your laptop or a server in your office closet, basically anywhere that isn't a massive data center. Foundry Local is essentially bringing the tools developers use in the cloud down to that local environment.
Okay, let's clarify the relationship here because we have Foundry and we have MAF. How do they fit together?
Good question. Think of it like a car. Foundry Local is the chassis and the engine. It provides the raw horsepower, the environment, the actual model execution.
Okay.
The Microsoft Agent Framework, or MAF, that's the transmission and the steering. It decides how to apply that power to get you from point A to point B without crashing.
I like that analogy. Okay, that makes sense. The article highlights 4 pillars of why you'd want to build this car in your own garage. The first one is obvious: privacy first.
Yeah, huge for enterprises. If you're a law firm or a medical researcher, you can't just paste client data into a public web model. With Foundry Local, the data never leaves the environment. It's, compliant by default.
The second pillar is zero latency.
No network round trips. If you're building something that needs to react in real time, like a voice assistant or maybe a manufacturing robot, you can't wait for a signal to bounce off a server 3 states away.
Right. And third is cost control. And this is where I have to push back a little. The article implies this is a money saver because there are no API calls. But hardware isn't free.
True.
You're trading API bills for electricity bills and hardware depreciation. You need a pretty beefy machine to run Qwen 2.5 decently.
That's a fair check. It is. You absolutely need the hardware up front. Probably a machine with a solid NPU or GPU. But the difference is CapEx versus OpEx.
Right. Capital expenditure versus operational.
Exactly. Once you buy the rig, the thinking is effectively free. You aren't going to wake up to a surprise $10,000 bill because your agent got stuck in a loop overnight. The operational cost is predictable.
That's a really valid point. Predictability is king in enterprise.
Okay.
And finally, rapid iteration, the ability to debug and fix things instantly.
Which is critical for developers. But here's the aha moment in the article, I think. This isn't just about saving money or securing data. It's about capability. By combining Foundry Local with the agent framework, you can build a deep research solution.
Okay, define that for us. What is deep research in this context?
It's an agent that doesn't just answer a question. It acts like a grad student. It searches, it reads, it realizes it doesn't have enough info, it searches again, synthesizes the findings, and then gives you an answer.
All autonomously.
All autonomously and all offline.
That is incredibly cool. But before we even get to the fun part of building the brain, the article stops us. It says step 1 is security.
It is, and specifically red teaming.
Now, usually when I hear red teaming, I think of cybersecurity experts trying to break into a network. But here we're talking about an LLM running on my laptop. Who am I protecting this from? Myself.
It feels counterintuitive, doesn't it? But Kinfei makes a strong point here. You aren't just protecting against you, you're protecting the agent from the data it consumes.
Oh, interesting.
I mean, if your deep research agent scrapes a poisoned web page, or if you copy-paste a malicious prompt from a forum, you need to know your local model won't go rogue.
Fair enough. So how does MEF handle this?
It provides a red team class right out of the box. It's automated adversarial testing.
I was looking at the attack strategies listed in the source. Some of these feel like throwbacks. ROT13, LeetSpeak, Morse code. Are we really worried about 1990s hacker tactics?
We have to be, because to an LLM, those aren't just hacker slang. They're tokenization exploits.
Tokenization exploits. Explain that.
Right. Standard safety filters look for specific semantic patterns, specific words. If a model sees the word harm, it blocks it. But LeetSpeak uses numbers instead of letters, like a 4 for an A.
So the model reads it differently.
Exactly. The tokenizer, the part of the AI that turns text into math, sees a completely different set of integers. It sees numbers, not the forbidden word. So it might bypass the safety alignment entirely.
Because it doesn't recognize the pattern.
Right. But the model's underlying logic still understands the intent and could generate a harmful response.
That makes sense. It's like slipping a note past the teacher in a secret code.
And Unicode confusables are even trickier. These are characters that look like a regular A or E to a human eye, but in the code, they're actually Cyrillic symbols or mathematical operators.
So to a standard filter, the sentence is just gibberish.
It looks like gibberish, so it lets it through. But the model is smart enough to figure it out.
So the red team class essentially fuzz tests the model with all these variations before you even deploy.
Precisely. It runs these attacks automatically, violence, hate, self-harm, and it generates a JSON file. The source mentions something like Quinn 2.5, 1.5b, redteamresults.json.
And what's in that file?
A pass-fail.
It's a scorecard. It tells you, hey, your model handled the violence check fine, but it failed when we asked it about self-harm in Morse code.
That is actually a really useful metric. Instead of feeling like your model is safe, you have a hard number. You are basically inoculating the model against malicious inputs before it ever sees real data.
Exactly. It ensures robustness. You don't want to find out your agent has a vulnerability after it's already processed sensitive legal documents.
Okay, so our agent is secure. It can handle a LeetSpeak attack. Now let's build brain. This is section 3. Designing the deep research loop.
This is where we move beyond the single prompt. The core concept here is research judge research again. It's an iterative loop. The article breaks this down into a cast of characters, or specific agents. So let's stress test this. Say I ask the agent, what is the current state of solid-state batteries in 2026? How does the data physically move through this loop?
Great example. So the first player up is the research agent. This is the workhorse. It acts as the interface to the search web tool.
So it fires a query to Bing or Google.
Exactly. It gets back a raw set of articles. But here's the differentiator. It doesn't just dump the text. It analyzes it, and it appends a self-reflection metadata tag.
Right.
It creates a little JSON object that says, here is what I found on range, but I found nothing on charging speed.
So it's self-aware enough to identify knowledge gaps.
Correct. And it passes that entire payload, the summary, plus the gaps, to the next player, the iteration controller.
So boss.
The logic gate, yeah. This agent isn't doing research. It is evaluating the quality of the research. It looks at that metadata. It asks the binary question, is this information complete based on the user's original request?
And if the answer is no,
it triggers a feedback loop. It sends the job back to the research agent, but this time it modifies the instructions. It says, go back out there, but this time search specifically for solid-state battery charging speeds 2026.
Now, I've built loops like this before, and the danger is always that they never stop. The agent just keeps researching the history of batteries forever.
Which is a very valid concern. That's why the controller has a max iteration parameter. It acts as a circuit breaker.
A safety valve.
Exactly. Even if the data isn't perfect, After, say, 3 loops, the controller forces a handoff to the final player, the final reporter.
And what does the reporter do? Just clean it up.
It's the editor. It takes the messy notes from rounds 1, 2, and 3. It deduplicates them, checks the citations, and compiles everything into a structured, readable report.
And the magic glue holding this all together is the workflow builder.
Right. The source code shows how you connect these agents like a flowchart nodes and edges. You define the logic. If the controller says continue, follow this edge back to research. If it says complete, follow that edge to the final report.
What I find so interesting here is the modularity. The expert in the article points out that this makes the system really testable.
Oh, that's the key benefit. You can swap out the brain, say, upgrade the model from version 1 to 2, without breaking the tools or the flow.
Or you could give the research agent a better search tool.
Without changing how the controller works at all. It's like Lego blocks for intelligence.
All right, buy the architecture. Makes sense on a whiteboard.
Mm-hmm.
But I've built multi-agent systems before, and usually they are a nightmare to debug, just a total black box.
Mm-hmm.
If the agent hallucinates or if the report comes back with the wrong data, how do I know which agent dropped the ball?
That is the exact pain point Kin-Fei Lo tackles at the DivUI.
Step 3 in the article. This sounds like a visualization tool.
It is a game changer for local development. I mean, if you're used to scrolling through thousands of lines of terminal logs to find one error, this is the antidote. The DevUI visualizes the workflow topology.
So you actually see the map of your agents on the screen.
You see the nodes and the edges we just talked about.
Yeah, and it's interactive.
Very. You can watch the step-by-step execution. You see the input go into the research agent. You see the output it generates, and you see the controller make its decision. You can actually see the path light up as it runs.
The article mentions real-time injection. That sounds like something out of the Matrix.
It basically allows you to pause the simulation and intervene. Let's say you want to test how the controller handles a specific weird edge case. You can pause the workflow right before the controller acts, manually change the input data, maybe inject some conflicting information, and see what happens.
So you can force errors to see if your logic holds up.
Exactly. The example they give is testing a comparison prompt. GPT 5.3 Codex versus Anthropic Claude 4.6. You can use the DVY to watch the research agent evolve its search keywords over 3 rounds.
And check if the final report actually covers both models.
You got it. It turns code into something visual and tangible. Instead of guessing, you can see exactly where the logic breaks. It drastically shortens the loop between it's broken and it's fixed.
Okay, so it works, it's safe, and we can debug it. But is it fast? Because running AI on a laptop usually implies hearing your cooling fan sound like a jet engine taking off.
That brings us to step 4, performance and optimization. The article discusses integrating with .NET Aspire.
And for those who haven't used it, .NET Aspire is primarily an observability stack.
It is. It wraps your application in OpenTelemetry to give you enterprise-grade metrics. And for an agent workflow, this is critical because slowness can come from 3 very different places.
Okay, break that down. If my agent takes 45 seconds to answer, what am I looking for?
Well, first, you look at model inference time. This is your local hardware. Is your GPU struggling to spit out tokens? Is the model just too big for your machine?
Right.
Second is tool invocation overhead. This is the network. Is the web search API hanging? Is it taking 10 seconds just to get a response from Bing?
And the third.
End-to-end latency. This includes all the handshake time between the agents.
So Aspire gives you a waterfall chart where you can see exactly which block is the bottleneck.
Exactly. And you might find out that your model is actually super fast, but your search tool is timing out.
And if it is the search tool, the article suggests specific optimization strategies.
The big one is caching.
Which is just good hygiene, really.
It is, but in an agent loop, it's vital. If your agent decides to search for Microsoft Agent Framework in loop 1 and then decides to search for it again in loop 2, you shouldn't have to hit the API twice. Cache the result.
It saves time, bandwidth,
and ensures consistency. They also mention model size. The example used throughout the source is Qwen 2.5 1.5b.
So 1.5 billion parameters. By 2026 standards, that's quite small.
It is, but for a specific task like summarizing search results, it's plenty powerful. Using a massive 7dB parameter model for that would just be a waste of resources and time.
It really feels like this is moving the project from a cool science experiment to something you could actually run a business on. You're making data-driven decisions on performance.
That's the goal. You aren't guessing if it's fast enough. You have the charts to prove it.
So taking a step back for a moment, we've gone through the technical steps, but Section 6 talks about a paradigm shift from model to agent.
This is the synthesis of everything we've discussed. Kin-Fei Lo describes 3 layers of modern AI development.
Let's break them down.
So layer 1 is the model layer. That's the raw engine. In this case, it's Foundry Local running Qwen 2.5. It's just the thing that predicts the next word.
The engine under the hood.
Layer 2 is the agent layer. That's the logic and the tools. The research agent plus the ability to search. This gives the model arms and legs.
The driver.
And layer 3 is the orchestration layer. That's MAF. That's the workflow that manages the entire process.
The traffic control.
Right. And the big shift here is that developers are no longer writing manual loops. They aren't writing while loops in Python to manage the conversation state. They are using a framework-first approach.
Which means?
It means they focus on the design of the workflow, the topology, not the plumbing. The framework handles the error handling, the tool calling, the state management for you.
The article also touches on extension directions. Where does this go next?
Well, the future applications are wild. They mention multi-agent collaboration, so adding a data analyst agent or a code generator agent to the team.
So your research agent could find the data, pass it to a data analyst agent to make a chart, and then the reporter agent writes about it.
Exactly. They also mention knowledge-base integration. So connecting these agents to vector databases full of your private documents.
Meaning it could read your company's entire archive of contracts.
And human in the loop. For critical decisions, the agent could actually pause and ask you, hey, I found this ambiguous clause. Should I proceed?
It's really blurring the line between software and, well,
a coworker.
That's the ultimate promise of agentic workflows. It transforms the computer from a tool you use into a partner you work with.
So, to summarize where we've been today, we started with the cloud dilemma. We found a solution in Foundry Local and the Microsoft Agent Framework. We learned how to red team our agent to keep it safe from leet-speak hackers and tokenization exploits. We built a deep research loop with a team of agents passing metadata back and forth.
We visualized it with DivUI to stop guessing at bugs, and we optimized it with .NET Aspire to separate inference time from network lag.
We have effectively gone from just a local model to a fully secure, observable, deep researching agent workflow.
And for the listener, why does this matter right now?
Because this is the path for enterprises and individuals to use AI without compromising. You don't have to send your sensitive data to the cloud. You can build systems that are open and composable. You own the stack.
It empowers the edge.
It creates a flexible architecture of cloud edge collaboration.
Here's a final provocative thought for everyone listening. The source mentions that the future isn't just the cloud, it's this collaboration. But think about this. If your computer can now do deep research while you sleep, completely offline, what other expert agents could you install on your laptop next week?
That is the question.
Could you install a lawyer agent, a doctor agent, a financial planner? If the software can research, judge, and report autonomously, the line between app and employee is getting very, very blurry.
And if that employee lives on your hard drive, who is responsible for its decisions? If your lawyer agent misses a precedent because of a caching error, who gets sued? You or the developer?
Questions we will likely be exploring in future deep dives. Thank you so much for walking us through this.
My pleasure. It's an exciting time to be building.
It sure is. Thanks for listening, everyone. See you on the next deep dive.